for like 20 minutes, and then I was like, yeah.
No, that's
I got the vibe, and then
Yeah.
move on.
a lot of analytical is. Professors do share the best one-liners, the best student analysis that we get. This was a good one this year.
Severely limited.
Severely limited by my lack of understanding.
For that answer.
Right, you get more points than not answer.
You get published.
Yeah, you get published on Twitter.
So,
How's it going?
you made it back.
Oh man, we had snow like up to our hips in the driveway.
Well, you're
Yeah, I'm like at the top of Kingsbury. And normally we like get out and snow blow during the storm, but we didn't get back until yesterday. So,
Yeah,
whew, it was fun. Thankfully the kids were in daycare, so
that helps.
yeah, we didn't have to worry about like entertainment. But then the power was out from like 3 o'clock until 2 a.m. So that was fun too.
Welcome back to the mountain.
I know.
Should've
Like,
kept trees.
man. But they say it's gonna be back like up to the 50s.
Yeah, if you got a south-facing driveway, you'll be fine. By the end of the week, everything will be melted.
Yeah.
Ours is angled just right. It's like straight south-facing with no trees on the other side, and it's slanted that way. And so you get like, I have to like shovel one strip. And by the end of the
Did you know
first
that
day.
when you bought it? Is that was
No,
the deciding
But
factor?
we will be looking for that if we ever move again.
Yeah.
We'll be looking for the south-facing driveway with no trees across the street.
That's awesome.
Also means we have a really good view of all the planets during the summer.
Oh, cool.
So Kathy can't use Heavenly's parking lot for astronomy, is where they usually go to set up a big telescope.
Really? Your
They
driveway?
might be using our driveway, yeah.
Oh, that's cool.
Wow.
But yeah, I got an email from her that, like, are you available on these dates? We're going to Shuttle Island's house.
Cool.
I think it's like, on her end, it's pretty confirmed.
Okay, that's fine.
That's what you get confirmed from the students.
Surprise.
I kind of expect, no, I share an office with her, yeah. She'll let me know. Cloud seeding. Cloud seeding is a cool environmental engineering thing that people have been working on. Actually, it was first postulated that you could induce precipitation in like 1876.
Wow.
In Europe, they had this idea that if you had areas of the atmosphere that had a lot of moisture to them, or that had some cloud formation, by giving additional nucleation points, you basically treat the clouds like it's a supersaturated solution. You give it a seed crystal, and that can cause additional crystallization or additional condensation to happen. And you basically make the cloud, the water molecules, the water particles in the cloud, you make them big enough that they turn into rain by just giving it a little additional nucleation points. And so the most common way to do that is silver iodide. I haven't heard of potassium iodide. That doesn't make as much sense to me because potassium iodide is soluble in water. Silver iodide is insoluble in water and relatively harmless to people. And you don't need very much of it.
That was a Wikipedia source, so I just
Yeah.
that one off the top of my head.
Dry ice is what they used to use. And that has the additional, my gut instinct is that's going to be helpful mainly because if you drop the temperature locally, you can pull more moisture out of the atmosphere because you lower the saturation point, because remember, gases are most soluble at higher temperatures. Sorry. If you have a liquid dissolve in air as your solution, if air is your solvent, if you drop the temperature, there's a lower, 100% humidity has less moisture in it as you drop the temperature. So if you drop the temperature using dry ice, you could conceivably pull more condensation out of the air. But I think mostly these days they just use silver iodide, tiny nanoparticles of silver iodide, and basically spread them into an area that they know has a lot of moisture, and get more water droplets to form, and you can increase precipitation just by doing that. I mean, obviously, and I actually, the number one source I found besides Wikipedia on this was actually Nevada. There's a Nevada agency that's doing this and has been doing this for about 20 years and documenting the results, and they've had a pretty substantial increase in precipitation in areas that are traditionally would be in a drought. So it's effective, and basically it's a way to, we can't change the total amount of moisture in the air, but we can change where it falls as rain by doing this. So it's a little bit like pulling water out of a river upstream. You're going to decrease the amount of water downstream, but you can use it where you choose then. It doesn't really, in theory, it's going to absolutely have some effect on health and environment, but at the same time, silver iodide is really stable. It's not soluble in water. It's not all that soluble in the bloodstream or in people. So it's not really all that different than any other small particles of solid that are insoluble in water. So it'd be, similar to microplastics perhaps, in terms of it's not great to get it in your body or for the environment, but it's also, there are bigger issues, and probably drought is probably a larger issue to health in most areas, especially in Nevada, than having a little bit more of these microparticles.
I feel like silver
2 feet
iodide-
of, I mean, 2 feet of fresh powder, zero toxicity.
I feel like silver iodide is one of the photo paper kind of.
Yeah.
So I don't know if I would call it safe.
It is once you film the silver iodide. So when it's it'll react with light to some extent. And if it encounters, I'm trying to think of which one's going to have lower solubility, but it might react to form different silver compounds, but silver is really insoluble with pretty much anything. So it might just be that as it reacts, goes from being silver iodide to being silver chloride, which is still insoluble in water. There are other things, because we have lots more chloride in the environment than we have iodide normally. So it's possible it's just turning into another. It will degrade over time, but not in terms of making any sort of toxic byproduct, especially at the levels that we're using it. But then again, it's all about trade-offs as well. So it's like, well, is this the most dangerous thing we're doing to the environment? Absolutely not.
Sean, what's the health food stores were rocking probably 15, 20 years ago? They were getting gray from the human skin. Was that silver iodide, or it was some sort of silver?
The
Colloidal silver?
Colloidal silver.
It's an alternative health.
Yeah.
Yeah.
It's not particularly good for you. Silver in general is not particularly good for you in the body. At tiny concentrations.
Similar compound?
So colloidal silver is when you take the nanoparticles of silver or silver iodide and you make it basically into an emulsion, which is going to increase how soluble it is in the body, which is not a good thing. It's, metallic mercury is bad for you, but organo mercury is way worse for you because it dissolves into your lipids and things much better, your cell membranes. So colloidal silver is not nearly as toxic as mercury, but it's still toxic. It's still a heavy metal. And putting it into a form that's more soluble in your body is probably not a good thing. I don't think it actually caused any deaths or anything, but at the same time, it was just a health food trend, bad, which usually, a lot of ways. Acid rain is one that's been around for a long time. We don't have it on the West Coast nearly as much as the East Coast, because the East Coast was still doing a lot of manufacturing back in the 70s and 80s, and they were burning coal without having red purification techniques. So the stacks that you see, the big smoke towers, that you see on coal power plants, they're there to they basically have a charged plate that runs up and down the middle. It's got a positive charge on one side and a negative charge on the other side. Anything that's charged that is produced by burning coal sticks to one of those plates. They didn't used to have that, and they would burn coal that had high sulfur content to it, and they would make a lot of sulfur dioxide and sulfur trioxide gases, and not have that plate that essentially removed it from the smoke before the smoke was released into the air. And so you wound up with a lot of sulfur oxides in the air, which when those react with water, sulfur trioxide plus water, you just take that as a combination reaction, add it all together, what do you get? H2SO4. So acid rain was literally sulfuric acid in the clouds as a result of burning coal that had lots of sulfur in it. So now we don't burn as much coal. We treat the smoke better. It's basically the power plant version of a catalytic converter to basically treat the product before it's released. And actually, LA did have some acid rain because back in the 70s, they also had, before they were catalytic converters, there was sulfur in gasoline too. You had similar stuff happening in LA, which is one of the reasons why LA was so nasty in the 70s and 80s. Or the whole valley down there, really, everything down there. And so literally you just get rain that has sulfuric acid in it and is significantly more acidic than rainwater is supposed to be. And so that in turn acidifies streams and lakes, which affects ecology and wildlife, as well as doing things like bleaching, paint on houses or cars and killing plants and stuff like that as well. So acid rain is not nearly as much of an issue anymore because we're treating the smoke better and we're burning less coal. But it's still an issue. And it was literally just that acid rain. It wasn't getting down into areas where if you got it under your skin, you could feel it burn you. But we're talking like pH of like 6.5, where rainwater is supposed to be about 7.5. So significantly more acidic than it was supposed to be. And remember, pH is a log scale, right? So that's 10 times more hydrogen ions than normal, right?
So I understand the idea behind electric cars, but I understand they require quite the immense battery. And then I look at pictures of lithium mines, and I kind of second guess myself if that's the best route to go.
So yes, lithium mines are also their own environmental disaster potentially, but it's a confined environmental disaster as opposed to being a global one in terms of CO2 levels and climate change. So yes, there are issues with that, and plus there absolutely needs to be something, and all completely green energy sources have the same problem. What do you do when the sun's not shining? What do you do when the wind's not blowing? You have to store energy somehow, and at this point, the best way we have of doing that is and even as bad as those lithium mines can be, once we get enough lithium, it actually is a pretty good closed loop as far as being able to recycle old lithium ion batteries. So getting us up to that point is going to be an ecological challenge to try and not make things too much worse. But at the same time, once we get that lithium, it's a lot easier to keep using that lithium as opposed to, have you ever seen the way they mine coal these days? Basically cut off the top of a mountain. They don't go in and dig in coal mines anymore. They literally cut off the top of a mountain and just break it up into rubble and sift through it. And then all the stuff, the chemicals that they use to pull the coal out washes downstream. You wind up with entire, like if you look in eastern Kentucky and western West Virginia, there's like nothing that lives in the streams anymore because those are so bad. So lithium mines are bad, but they have their runoff issues, but it's not nearly as bad. in my opinion. If we were talking 10, 15 years ago, I would be pushing even harder for nuclear, because nuclear is not even as bad as mining lithium in terms of mining uranium and enriching it to power plant levels. Is actually a lot better for the environment. But the turnaround and the amount of time it takes to get a nuclear power plant up and running is such that if you started building one now, renewable, truly renewable green energy, it's probably going to be caught up before your power plant actually gets its return on investment. So what we should have done was, in the 90s, we should have built a bunch of nuclear power plants. And basically, we could have gotten rid of coal power and natural gas power plants then by 2000. And then now we would be just looking at how do we switch from nuclear or supplement the nuclear with more solar and wind power. And then that gives the advantage of a smart grid, right? Anything where if we don't have sun or wind for a while, the nuclear can pick up the slack, because nuclear power plants produce about the same amount of energy regardless of any external conditions. All right. You guys asked good questions this week. Transdermal medications. So there are lots of what they call routes of administration, ROAs, for different drugs. Transdermal is one that seems like it could be less harmful, and so it's marketed as being like, well, this is better for you than smoking, and they're probably right. But it's basically, if you're trying to get medicine to absorb through your skin, it has to be the right medicine. You have to put it in a high enough concentration on the right spot on your skin. There's got to be some place where the blood veins are really close to the surface, where the skin is thin, and it has to be something that's pretty non-polar, because it has to move across all those cell membranes. So it has to be the right situation. But it does give you some advantages. If you just eat something, the first thing, if you absorb something into your bloodstream from your stomach or your intestines, the first thing your body does is send it to your liver to get cleaned up, because it doesn't trust anything that comes from your digestive system, with good reason. And so you actually wind up basically filtering out a good chunk of your medication if you take it orally. Versus if you take it in other routes, such as smoking or inhaling or IV or transdermal or sublingual, which is under the tongue, you bypass that liver the first time through the bloodstream. So you actually get a higher percentage of your medication into the bloodstream. But it depends a lot on what the chemical is, how soluble it is in water, how soluble it is in fats. Basically, all drugs will have their own sort of, you run a bunch of tests, like, okay, the bioavailability of this compound with this route of administration is 90% versus 70%. And bioavailability is just how much of the medication makes it into the bloodstream compared to how much you used. And so it's really going to depend a lot on what the drug is, what the route of administration is, and sometimes there's an advantage to having things go through your liver once. But that's one of the reasons why some drugs you can't just take orally, because the liver is too good at filtering that compound out, or you're using it in small enough concentrations that your liver just eliminates it that first time through, and none of it ever hits the rest of your bloodstream. That said, if they're not providing any sort of numbers, they're just saying it's better, it's just marketing. Forever chemicals. So this is an interesting concept, this last sentence especially, converting waste into less harmful chemicals. Or even better, is converting the waste into something that can then be reused. And so that's a concept called chemical recycling. Most recycling that's done already is physical recycling, where you take a compound you chop it up or you purify it and you put it back into the same state it started in, and then you can reuse it to make something else. That's really easy with stuff like aluminum, and glass. But chemical recycling is when you actually take something and then process it in a way that turns it back into a precursor, that turns it back into a raw chemical that can then be reused. So instead of taking one type of plastic, shredding it, turning it into a park bench by just basically compressing it, you take it and you break it back down into the raw pieces that you made the plastic from in the first place. So that's actually sort of the next wave of recycling. There's a lot of research going into chemical recycling at this point. One of the problems is one that's kind of a new idea. There just hasn't been a demand up until the last 30 years or so for that. It's always just been cheaper to make your own, just make new stuff, rather than chemically recycle old stuff. What's that?
We're gonna run out.
We're gonna run out? Yeah. Well, I don't know, if we just stop burning fossil fuels, then we have more fossil fuels we can use for chemical precursors. But no, so it's a relatively new concept, and one of the other issues at this point is it's way more subject to the purity of your waste. Because if you are trying to get something to go through a chemical reaction to get it to be purified or turned back into something useful, the wrong thing mixed in there, a little bit of aluminum mixed in with your plastic that you're trying to convert into something else, could give you a totally different product, as opposed to just having, you got a little bit of aluminum in your shredded plastic that you then compress to make a park bench. So what? It's still the same, it's still going to give you the same product more or less, versus having a little bit of aluminum when you're trying to get this organic material to react. Aluminum affects a lot of chemical reactions. And so it's a lot more subject to, you really need to make sure that what you are putting into the chemical recycling is really pure, or else you wind up causing a lot of damage to the facility that you just built or the environment around. And so it hasn't taken off as much because at this point it's not as economically stable or viable. That could all change because there are some things that are easier to take waste and turn back into. So it's basically the most expensive plastics and the most expensive things like solar panels or different compounds that you use to make some of these lithium-ion batteries. Those are now expensive enough that that's worthwhile, versus things like plastics and glass and aluminum and paper, not so much. Brad?
So, do you have any thoughts or ideas on how that could partake? Because, if I'm thinking about taking something and reacting with something else to try and get the product that you want, I feel like that can be either potentially problematic or just complicated in general.
Especially when you get into the fact that different brands of nonstick pans have slightly different formulations of nonstick polymers. They're not all going to react exactly the same way. And so one brand is going to give you a slightly different product potentially, and that's a problem. You don't really want to have that issue. So a lot of it has to do with taking a commercial product where the exact formulation is a trade secret and then trying to turn it into something consistent, regardless of which brand you started from. So yeah, there are a lot of things to get ironed out with that. And really, it's probably going to be used mostly for the most expensive elements. Plastics, less so. What's going to be more likely with plastics is that we wind up with some forms of bacteria that are capable of breaking down plastics. Eventually, there's already happening in some places in Japan, in some landfills in Japan. They found some bacteria that have evolved to break down a certain plastic. And basically the problem is plastics have only been around for like 70 years or so. And that's a lot of generations of bacteria, but evolution is slow. So eventually that will be the case. It's the same thing that happened with, lignin is the compound in trees that makes trees grow tall versus shrubs that stay low. And when trees first appeared evolutionarily, there were no funguses or microbes that were capable of breaking down lignin. And so that's why we have petrified forests, is because trees would die and not rot. because there was nothing that existed that was capable of breaking down that plant matter. And so they just turned into fossils instead. And so plastics are sort of in the same boat right now. But evolution's happening a lot faster right now because there's a lot more transfer of information and microbes across the planet. So there's a lot more reproduction happening, a lot more evolution at the microbial level. So we'll see what happens with all that. That's probably the route that plastics will go, but chemical recycling will be a big deal for things like lithium-ion batteries, computers, getting the gold out of computers. There's actually more gold in landfills in Japan than there is in most gold mines these days.
Wow.
And actually, when they've had the Olympics in Tokyo, all of the gold medals and silver medals and bronze medals all came from landfills. They were able to mine that out of the landfills in Japan because there was so much electronic waste from the 70s and 80s. So, absolutely, that's absolutely the next wave of recycling, which is not quite there yet. All right. We will talk about these. Also want to, before I forget to mention it, we have a midterm coming up. This is week 6 already. It'll be next Tuesday is the plan. And actually, let me pull up the schedule so I can make sure I don't contradict myself. I believe we're looking at next Tuesday in class, but I might have put it in, no. Oh, I gave you till next Thursday. So a week from this Thursday, and your lab next week is exam review. So just like if you've had class with me before, I give you a practice test. You'll have a week with it. That'll be your assignment for this next week. Will be to go through the practice test and complete it, turn it in for points. And then next Tuesday in lab, you'll be able to work with Carl on getting some help on some of the concepts you're struggling with. I don't know exactly what the material is going to be yet. I have to double check to make sure we actually got through everything that we're supposed to get through so far. This is an old schedule I'm looking at because we're already a full week behind on this, but we're not going that much slower than last year. So I'll make sure that the practice exam, it reflects that, and we won't cover everything that's on the syllabus by then.
And we'll take it like in here during class time on Thursday?
Yes.
Okay.
Week from Thursday in class, 2 hours. It won't be set up the way I usually try to do tests, which is 10 sections, each worth 10 points. That's just, OChem doesn't lend itself to that structure because we only have a couple major areas we focus on. And so it'll be set up a little bit differently points wise, but you'll see the formatting of that on the practice test. So it still shouldn't be a surprise.
We can use our lab partners during the test, open book.
It won't be open book. And you don't want it to be open book. Because the way to make an open book test is you just make it really hard. And frankly, that's not what you want at this point in OChem. We'll get to that point where it's easier to have an open book than it is to do a closed book test, but we're not there yet. Well, how come we get some molecules that form rings rather than chains? Well, sometimes if you look at the formula for cyclohexane, it's C6H12, right? But N-hexane is C6H14. If we're talking about these things forming through natural processes, the actual ratio of carbons to hydrogens actually can control which of these you form. If you only have a 2-to-1 ratio of carbons to hydrogens, you're not going to make hexane. You might make hexene because adding a double bond removes 2 hydrogens, right? Because you took a bond that was a carbon-hydrogen bond and turned it into another carbon-carbon bond. So each of these two carbons just lost a hydrogen when you make a double bond, right? So if you have a natural process that can make cyclohexane, it also will probably make some cyclohexene as well. You get a mixture of different products that all have the same ratio of hydrogens to carbons. And so, when I mean, say natural process, I mean non-biological process. And so that's what you get. That's why we buy gasoline as a mixture of different compounds that have about the same formula as octane. But it's not just one compound because, what are fossil fuels? They're just leftover stuff that's stewed underground. They're leftover biological material that's stewed underground for X millions of years until they turn into this goopy mess. And so when you separate it out by doing distillation, you get a mixture of things based on how many carbons they have. And is going to be the number one thing controlling their boiling point. So you actually get a mixture of all these different C6 compounds. If you go into the stockroom, if you look in the flammable cabinet, we actually have a bottle marked mixed hexanes, or hexanes plural. It's because it's just a bunch of things with 6 carbons and 14 hydrogens arranged differently. All the constitutional isomers that have 6 carbons with 14 hydrogens, because they're all going to be about the same boiling point. So we just throw them in a bottle together and it makes a good solvent. It's not very good if you actually want to react it to make a predictable product, though. So it's just a matter of why do we get rings versus chains, stability, and how many hydrogens are around versus how many carbons are around. And that will also govern how long the chain gets, too, right? Because different carbon chains are going to have slightly different ratios. If this is C6H14 versus if it was pentane, it'd be C5H12. Right? Slightly different ratios is going to govern whether you make pentanes versus hexanes. If we're assuming that all of these possibilities can happen at the same time. And it's just going to be a matter of the statistics and what's most probable based on what's your ratio of hydrogens to carbons. If we're talking biologically, then all bets are off. Because biologically means you've got enzymes involved, you can put in extra energy by using ATP or other energy sources. All sorts of things can be different because you're actually inputting external energy, and that affects all of those probabilities. This question, just how well can we predict mathematically what sterics look like? The answer is very, very predictably. Computational chemistry is entirely based on this. My branch of computational chemistry when I was in grad school was called ab initio, which in Latin means from the beginning. Ab initio calculations means you're starting from quantum, and beyond speed of light and Planck's constant, you don't put anything measured into it. It's all based on fundamental knowledge of atomic orbitals and quantum mechanics. And so we're actually going at the orbital level to figure out things. But you can then turn around and use those orbitals to figure out what the most stable geometry is. Because those orbitals affect the sterics, right? The shape of where your orbitals are determines what's bumping into other things, because most of the space is electrons. So we can do it pretty well at the ab initio level. You can actually do it at the protein level, though. You use a different branch of computational chemistry called molecular dynamics, which is basically you don't go all the way at the individual orbital level. You say, okay, well, this amino acid has a side chain that's this size with this partial charge here and there. And you basically just say, okay, well, that means if you put it next to a bunch of other amino acids with these properties, they're going to naturally arrange themselves to minimize sterics and to minimize negatives bumping into negatives and positives bumping into positives. And you basically just tweak it and you shake it until it winds up into the most stable configuration. We can actually estimate, just based on what the protein or the sequence of amino acids is, we can estimate what the most stable configuration of a protein is, just starting from the amino acid sequence by basically, it's like put it in the box and you shake it until it doesn't move anymore. Because and just call that, well, that's probably our most stable state or close to it. It's not perfect, but it's pretty good, and you can estimate a lot of things that way, predict things, or use it to explain enzyme mechanisms and things like that. I'm partial to this one because they use a lot of measured things in here, make a lot of approximations. We make very few approximations here because the math is more rigorous. But yeah, we can absolutely do this in computationally and even by hand to some extent. You burn something and then look at how much energy was released compared to something that's less sterically hindered. You can get an idea of how much energy is bound up in those sterics. And then last but not least, can you tie a knot with a long alkane? You absolutely could in theory. Practically speaking, it's kind of hard to do that. You basically have to start with an open chain, connect the two ends through something that's already existing, right? So it's doable. We don't have the ability now, but basically it's a form of nanotechnology. Nanotechnology is basically making structures at the molecular level, making consistent structures at the molecular level. We're not at the point now where you could daisy chain cyclohexanes together, but it's certainly something that's conceivable in the future. That would actually make a really interesting polymer if you were able to do that, because it's something we have to be very, very flexible and very, very non-polar and still have a lot of similar properties to a lot of plastics. We're just not quite there yet. But that also reminded me of, I saw this the other day. It's a compact way of representing tetradecane. So 14 carbons. You arrange it just right, it looks like a SUSY symbol, which apparently is still around.
Do kids still think it's as cool as we thought it
They
was?
do, apparently. I don't know if it's like making a comeback, if it's like I'm now so old that I'm retro, or what, but apparently it's still around. But yes, in theory, you can make some pretty complex shapes and structures using nanotechnology. At this point, we're just mostly at the stage of making carbon nanorods, which is basically if you take a flat sheet of graphene, which remember is a bunch of connected benzenes. If you basically have this repeating indefinitely in all directions, you can wind up with taking this sheet, folding it like a piece of paper and connecting the two ends and making a tube out of it, which is what a carbon nanorod is. It's basically when you have this tube that you make, and it has very interesting properties. For instance, it's fairly conductive for an organic material. It's carbon nanofiber, carbon fiber, not just carbon fiber. Carbon nanofiber, and what's the term they always gets thrown around as a potential use for a space elevator? Carbon, maybe it's just nanotubes. Basically, but if you could visualize making a these things have a really good strength to weight ratio. So in theory, you could do something like make a really strong cable out of it, something that you could tether a satellite in a geosynchronous orbit, and then use this to basically send things up and down without needing a rocket. It's the idea of a space elevator. You just make an elevator that goes up to a space station that's at the right height for it to be a geosynchronous orbit.
Wow.
But you need something with enormously strong tensile strength. Tensile is how strong is something when you pull both ends of it. And carbon nanofibers have been used as an example of something that has enough tensile strength, you just can't make them long enough yet. Spider silk is the other one that gets always used as an example because it has a really good tensile strength for its weight, but we can't produce it in large enough amounts and long enough samples. All right, now let's actually do some review. We ended with this the other day. So remember that a asymmetric center is anything where you've got 4 unique substituents attached to the same atom. Remember that in order for it to have 4 unique things in 3 dimensions, that means you're going to have something where the mirror image is not the same as that molecule. You won't be able to twist it around and reorient it and make it turn into the same compound. And so our smoking gun for an asymmetric center, where we have to be worried about this, is 4 different things. And when I say 4 different things, 4 things you can tell the difference between attached to the same carbon or the same atom. Carbon is the most likely atom for this because carbon forms 4 bonds when it's stable, right? And so usually it will be a carbon. None of these carbons fit, right? Any sp2 carbons aren't going to ever be chiral, aren't going to be asymmetric centers because they only have 3 things attached to them. So anything you've got where you've got a pi bond, you can basically eliminate it. It's not going to be chiral. So that means these benzene rings are out. This carbon, how many things does it have attached to it? I mean, it's got 4 bonds, but one of them is a benzene ring. The other that we have drawn is the rest of this molecule. What are the other 2 bonds on that carbon? Hydrogens, right? Anytime you've got 2 hydrogens, it's not chiral because the hydrogens are identical. If we did something weird, like we replaced one of those hydrogens with deuterium, with a different isotope of hydrogen, now we can tell the difference between it, even though it's the same chemically. So, not an asymmetric center. This one is going to be an asymmetric center. You've got one of the bonds is straight to a benzene ring, one bond is a carbon and then the benzene ring, so those are 2 different things. Then you've got an oxygen, and then you've got the rest of this molecule over here, so 4 things attached to this carbon. Oxygens are easy to eliminate, because what do they have that's the same? If an oxygen is neutral, how many bonds does it have?
6.
It has control of 6 electrons,
Yeah.
which makes it, so let's say we're looking at methanol. The oxygen is attached to a hydrogen, and carbon. So oxygen is neutral, has 2 bonds. The other electrons are lone pairs, right? We can't tell the difference between the lone pairs. So oxygens, if they're neutral, are never going to be an asymmetric center. Because if they're neutral, they have to have 2 lone pairs, and 2 lone pairs, by definition, is going to be symmetric. It's going to have symmetry to it. So oxygens are really easy to eliminate. Anything where you've got CH2, gone. CH3, gone. That's a CH3, that's a CH2, those are CH3s, those are all not asymmetric centers. We can eliminate them. As soon as you can point to it and say it has at least 2 hydrogens, throw it out. It's not an asymmetric center.
Is that, okay, I know you don't like dealing in absolutes, but is that an absolute?
Yep. If you can't tell the difference between 2 of the things attached to the atom, it's not an asymmetric center. And I can deal in absolutes for that one because that's the definition. If it has 2 things you can't tell the difference between, it has symmetry. If it has symmetry, it's not an asymmetric center. Nitrogens you have to be careful with because nitrogens, when they're neutral, only have 1 lone pair. So nitrogens you gotta watch out for. I keep using this one so it's really not tracing things well. Conceivably, you can have a nitrogen that has 1 lone pair, a hydrogen, a CH3 group, and a CH2 CH3. You can have a nitrogen that has a hydrogen, a lone pair, a methyl, and an ethyl. And in a skeletal structure, we might only draw 2 you have to remember that nitrogen's got that lone pair when it's neutral. And that lone pair takes up space, right? Just remember back in Vesper geometries. So if it takes up space, you got 1, 2, 3, 4 different things taking up space that we can tell the difference between. So you got to watch nitrogens, they're tricky. But in this case, that nitrogen has a lone pair. It's got this whole molecule here, but these two are identical, right? Both methyl groups are identical. So as soon as you can't tell the difference between two of them, it's not asymmetric. So that carbon with asymmetric center, and that one. This carbon has a methyl attached, it has this nitrogen group attached, it has all this attached over here, and then it has a hydrogen that's not drawn. So for carbons, if you have three unique things drawn, that means your fourth is going to be a hydrogen, and it's an asymmetric center. It takes a little practice to be able to see these. We'll keep working at it.
So that one that had the, I don't know how to word this. But I guess the one in the middle where it branches off, yes, that one. If that second benzene ring was a methyl group instead of methyl, it would not be an asymmetric center, correct?
So if the benzene ring was directly attached here, correct, because then both those benzene rings, we can't tell the difference between. But if anything was different about those two benzene rings, if one of the benzene rings had a chlorine hanging off of it, now all of a sudden we could tell the difference between them again. And we'll talk, and so here's one of the ways that you can, the way we name these, we actually have to have a way of naming these differently now, right? Because if you have 4 distinct things and the mirror image is not the same compounds, we have to have a way of writing a name that's unambiguous. I keep trying to use the wrong keyboard. All right, so I'm going to leave this up here and then we're going to work through some examples. Essentially, when we're trying to name these mirror images, they're called enantiomers, which probably means something in Greek, but I would guess it means something to do with mirrors in Greek. I'll check that out, right? But basically what we're trying to do is we're basically going to give a priority to all of the atoms, to all the substituents that are attached to our asymmetric center. And then we're just going to, we have to rearrange it so that we're going to point whatever's the lowest priority is pointing away from us into the paper, into the board. And then all we do is we count 1, 2, 3. And when you count 1, 2, 3, it's either going to go clockwise or counterclockwise. And so if you wind up with the priority going clockwise, we call that R, which I always think of it as being R for right-handed, but it's not R for right-handed because they use Latin and Greek names. So again, I'll have to double check that one. But I do know that if it's counterclockwise, it's called S configuration. And S stands for sinister, which is Latin for left-handed. I like to remind my left-handed brother of that.
Sinister.
All right, so let's work through an example. Let's say we've got actually we're going to deal with the compound you made in lab last week. Actually, wait, you made 1 bromobutane, huh? 2-bromobutane has an asymmetric center. Because 2-bromobutane, this is about the smallest thing that you can have. It's going to have symmetry to it. This carbon right in the middle, though, has a methyl group, has an ethyl group, has a halogen, and it has a hydrogen. So 4 unique things attached. So if we want to name this, if we're just naming it without worrying about enantiomer, we just say 2-bromobutane. If we want to say whether it's R or S 2-bromobutane, anytime you show the stereochemistry, show specifically whether a bond is coming out towards you or going into the board, it's usually because that's an asymmetric center. So we can't just name it as 2-bromobutane, we need to say R2-bromobutane or S2-bromobutane. The way we do that is by using this system. All right, so I'm going to blow up this carbon here, and so we can focus on that, because this is the asymmetric center. And just try to redraw it with everything in the same position it's in. So we've got a bromine going away from us. We've got a methyl group down to the left, an ethyl group down and to the right. And that means we've got a hydrogen sticking out towards us, right? So I just redrew our molecule, showing the tetrahedral shape and showing everything attached to the asymmetric center. We assign priority to each of these. Basically, we're going to replace, not replace necessarily, we're going to go through and number from 1 to 4, highest priority to lowest priority. And the priority just goes based on atomic number. So atomic number of whatever's directly attached to the carbon. So that means 1 and 4 are actually really easy to assign here, right? What's the highest priority? It's got the highest atomic number out of everything directly attached to the carbon. Bromine. Bromine's at 35, right? So bromine is our highest priority. What's our lowest priority? Hydrogen. Or the methyl and the ethyl, they both have a carbon directly attached, which means the same atomic number. So you don't just add up all of the atomic numbers and put them together. You do a tiebreaker. We start here, we go take one step, we get to a carbon here, we get to a carbon there. Those are the same. The tiebreaker is then, okay, go one bond further in the direction that has the highest atomic number. So if I redraw this as the complete structure, if I go one bond further on the methyl side, what do I hit? Hydrogen, no matter which way I go, right? Over here, I could go towards another hydrogen, but if I'm trying to win, I'm going to go in the direction that has the highest atomic number attached. So I get to another carbon. So after 2 steps, instead of just 1, I get to a carbon versus a hydrogen. That tells me this is going to be higher priority than the methyl group. All right, so it's always just start at the asymmetric center, take 1 step out, 1 bond out, and assign all the priorities you can. If there's any ties, you take 1 more step out. But you're not just looking at the total molecular weight of what's attached. That would be a totally different system, right? In molecular weights, or if you wind up adding things up, you can wind up with ties. You shouldn't ever get a tie if you use this system, unless they're the exact same substituent, and then it's not an asymmetric center. Right? If you had an ethyl and an ethyl, now all of a sudden it's symmetric, and then when we try to assign priority, we would get a tie. Brad, do you have a question?
No.
Okay. All right, so if we're trying to decide R versus S, we've assigned priority. Now the goal is we want to put the hydrogen into the board. without breaking any bonds. So by taking this and flipping it around somehow, we need to put the hydrogen into the back. We need to move everything else accordingly. And so there are a couple of different ways we can visualize doing this. The way that I usually find the easiest is to keep one of the 4 substituents in the same spot and spin the other 3 like a propeller, like a fan blade. You can visualize that with your tetrahedral model in front of you. Picture keeping one of the bonds the same. Basically, you're taking that bond and spinning it like this, like you're spinning a toothpick between your hands. The rest of this should all twist, right? So we need to do that in such a way that we're going to put the hydrogen into the board and then redraw it. So the way I would do this one is I would keep whatever's the biggest thing, just because I'm lazy and I don't want to redraw it as very much if I can avoid it. I'm going to keep the ethyl in the same spot because it's the biggest thing. It takes the most work to redraw. I'm going to take the rest of this and I'm going to rotate it around that bond. And if I go this way, the hydrogen's sticking out. If I rotate it, the hydrogen's sticking in, right?
Are we rotating into the board or are we rotating counterclockwise?
That depends on where you're standing. We're rotating the hydrogen into the board.
It's coming out of the board currently.
It's currently coming out of the board like this. And so if we're rotating around my thumb is the bond that we're keeping stable. We're rotating around that bond, we want to do that. Right? And so then when we redraw that, we'll get the hydrogen is now into the board. The methyl was in the plane of the board, and when we rotated it, we did that. We went from here to here with the methyl. So the methyl is now what's sticking out. The bromine is down here, and the ethyl is over here and didn't move. Everybody see visually how that's the same molecule, just twisted, rotated one spot? If you do this properly,
It's like hard to
it is.
do in my brain.
The fan blade analogy is the one that always works the best for me. The one you're keeping the same is the rotor in the middle of the fan. And then the 3 fan blades that are twisting are up here. And so you're doing this. Or you could keep this one the same, and I could twist it like this. And this is where, you weren't here last week, so I'll get you a molecular model kit. But if you, Ryan, pass that up to Miranda real quick. I want to call you Melissa. I'm sorry. I probably won't do that. So picture, put that blue one in this position and twist your fingers. Yeah. So let the rest of the molecule go.
Okay.
Now twist your fingers. Okay. Like that.
Okay.
What you just did. Like a propeller. If the blue is the ethyl group we're holding still, we're twisting around that bond. So we were like this. This is the hydrogen, this is the bromine. This is the methyl. When we twist it, we're doing that. So everything just clicks over 60 degrees. And I'll get you one of those kits too.
And you're using that rotary part just because you want to redraw it, what's the idea? You don't want to.
This is the way that makes the most sense to me. There's other ways you could take this. For instance, if we took this whole thing and we flipped it like a pancake, now the hydrogen would be pointing towards us, but we would have to redraw where everything is. We'd be taking it, and now we would wind up, if we flipped it like a pancake, we'd wind up with something that looked like this, where everything flipped, right? That works too. Visually, that might be something easier for you to see what's happening. Literally just flipped it like that. So what was down and to the left is still to the left, but now it's up and to the left. Down and to the right is now up and to the right. And these two are now pointed down and flipped. Because they were like this. When you flip it, my finger switched spots, right?
Yeah.
My index finger was pointed out, and this is the hydrogen, but flipping it, now the hydrogen's into the board. You have to get really flexible to do this, to teach everyone. For me, this is the way that rotating an electric propeller is the way that's the most consistent. It's easiest to treat just like it's a process. You keep one thing the same, you twist everything else. And so that's the way that I teach it first, but whatever way you can see it visually is fine. It's going to take some practice though. All right, so to finish this, and then we'll take our break and then we'll do some more practice. We still have our highest priority is now here. Our lowest priority is into the board. That's 3, here's 2. And hydrogen is 4, but again, once it's into the board, we don't really care about it. Now, all we do to finish this is you draw a circle from 1 to 2 to 3. So I said circle on the arrow. And when you do that, your arrow is always going to be either clockwise or counterclockwise. If it's clockwise, it's R. In this case, it's counterclockwise, so it's S. And so Brad made the point earlier, he said, well, are we twisting it clockwise? And so that depends on where you're standing, right? The whole idea with putting the hydrogen into the board, you put your lowest priority into the board because that gives you the right frame of reference. That tells you you're looking at the front of the clock instead of the back of the clock. Right? Because that clock's moving clockwise, right? If I took that clock and I flipped it over like a pancake, now I'm looking at the back of the clock, right? And now the second hand would be moving counterclockwise relative to where we are. So the whole idea of putting hydrogen away from us, putting lowest priority away from us, is to make sure we're looking at the front of the clock. It gives us a common point of reference.
Okay, this might be a little bit out there, but you just said relative to us, and I just couldn't help but think. You know, you're outside the train, someone's inside the train, and these molecules are moving. Are they going to be different to me?
If they're moving?
Yeah, if they're moving and moving themselves
As-
inside the train.
As long as all the atoms are moving the same relative to each other, not relative to me. Relative to me, it shouldn't matter. Because if the atoms are moving the same relative to each other, it shouldn't change.
Okay.
And even if they aren't, if they're twisting around and rotating around, you still are going to wind up with the same molecule because everything is still, even if it's still rotating relative to itself the same way. Right? So when I rotated the hydrogen back, the others had to rotate relative to the hydrogen because this pair of electrons is pushing on that pair of electrons. It's a good question. But it's not, this is one of those times where chemistry is not quite as complicated as it could be.
That's good.
And that's your, what was it, center, left-handed?
So sinister S.
Sinister, thank you.
So this compound we would label as S2-bromobutane. So just like cis and trans, we just throw that extra identifier on the front. R versus S, you just throw it right in the front. This would be S2-bromobutane.
And that's the one we rotated, correct?
And that's it's the same one. If we rotated it properly, we didn't change the molecule. That's the whole idea of being careful with that. We can't just flip the way these are drawn, because now it's not the same molecule. If we flip these, but we leave the methyl and the ethyl where they are, we broke a bond and reattached it. And so that's the whole idea with this rotating is we have to be careful that we're not coming up with a different molecule when we do that. All right, we'll do more practice with this in 10 minutes. Come back to 20 after. And if you feel lost right now, just or having trouble visualizing, this is the single trickiest thing to be able to visualize. This is the thing that trips up everybody when you first see it. This is something that will give you trouble for a bit. So you're in good company.
I cannot be stuck in back in a second.
That's something to eat. Forgot to grab a bar.
history of the Manhattan projects. The plural essentially makes scientists have to be both the superheroes and the villains.
That's fair.
This though, I believe.
There's, you've got Einstein, who's a drunk, you've got Feynman, who's a narcissist, you've got Oppenheimer, who's got multiple personality disorder.
Oh, that's so great.
He's-
Actually, I was at Berkeley discussing with somebody there about like the history of, development, atomic weapons. And,
This is great.
and it was like sort of, there was like a moment in the conversation where it was like, the use of the atomic weapons is not, it's not because of the science of developing atomic weapons. It's because of the people who got a hold of it, and it was their aim.
Well, and also, I mean, the scientists are not blameless in a lot of ways, especially a guy named Teller was instrumental in developing hydrogen bombs, and he was basically almost pathologically incapable of thinking that his invention could be harmful to humanity, that he was like convinced it was going to be a net positive.
Yeah.
And so he was a huge advocate at the government level for doing things like, oh, let's see what the moon's made out of. Well, we're going to launch a thermonuclear weapon at it and see what happens. Or, oh, you want a bigger harbor in Juneau, Alaska? Let's detonate a hydrogen bomb in the harbor, and that'll harm us a bigger harbor. He was definitely, there's a lot of that, but yeah, and most of the scientists though were absolutely. Well, I guess I shouldn't say that. It was a split within the Manhattan Project about whether or not what Truman did was the right option, because they didn't have enough fissionable material. They had enough fissionable material to make 2 bombs. They weren't sure that either of them was going to work. And so the argument goes, well, the Japanese didn't know how much we had, therefore we should have just done a demonstration on an island in the Pacific that had nobody on it. Say, hey, look over here, look what we can do now. Are you sure you want to keep fighting us?
Right.
But the downside to that is if you do that and your bomb doesn't work, you just, now all of a sudden if you drop it and it doesn't work, you run the risk of, 1, them getting to it first and reverse engineering it, and 2, losing half of your uranium or your plutonium. And so the argument was, well, at the very least, we need to make sure that it goes off once. And then Nagasaki happened basically because the Japanese didn't think that we could replicate it. And so they didn't surrender. We didn't give them enough time to adequately consider. And basically the people did more the war hawkish of the scientists that really wanted to know what happened with the plutonium bomb.
Right.
Because the first one was uranium.
I think is one of the more nice way to put it, more complex things.
Yeah, I think that's an appropriate way to put it. That
I have the same kind of feeling about Fritz Haber, and I feel that like a lot of, or at least I didn't get that feeling that Carl was the one who was kind of going there with the whole process and stuff. I didn't really get the feeling from him that he was like, also this guy totally sucks. It was just like, this guy's awesome because of chemical agriculture and development of using the fat-based principle to make a whole bunch of ammonia and stuff. But the same guy also responsible for all of the chemical weapons and used in World War I, like chlorine and phosphate and stuff. And he had the thing that I think is the worst aspect of Haber and his approach to that was that he was like, well, we're going to develop weapons and they're going to be used to kill people. So I don't think that it really matters how much people suffer before they die.
right. Yeah. And that's,
It's
I mean, that's
equally
one of the
inhumane
things,
to just
right,
kill people, so it might as well use these tools that my lab developed.
right.
And he was pretty strongly nationalist too. Like,
Yeah, even before Nazi Party was a thing, it was, it's probably what caused the most loss of life was not, the chemical weapons was opening a bit of a Pandora's box, but at the same time, chemical weapons, while horrific, you're still limited to killing people in the thousands at most.
and only downwind.
And only downwind. But probably what was the biggest drawback was the fact that when he came up with the Haber process, before that, the Germany and who we consider the bad guys in World War I, there were no good guys in World War I, but the losing side of World War I, were essentially blockaded to the point where they couldn't get ammonium nitrate, right? So they couldn't make more gunpowder. If that had just held, if he had just not, made his process public until the war was over, it would have been over in a year. Instead, because now that they weren't reliant on ammonium nitrate coming from South America, they were able to prolong it indefinitely. And so World War I went from 1911 to 1918 or something like that. You had a 7-year war with millions of people dying, as opposed to something that could have been over in 6 months. Had the Haber process not become public knowledge or was not scalable. So yeah, absolutely, it's one of those things where technology is neither good nor bad, but it can be very, very easily turned into an evil, a net negative for society if it's not used properly, which is one of the reasons why the Cold War was so dangerous. Because every new bit of technology that was developed from like 1945 until 1991 was immediately weaponized. The very first thing any government did with any new scientific discovery for almost 50 years was weaponize it. And even if it doesn't get used, that's still something that's a problem, where we have more negative uses than positive. All right, let's do some practice with these. So two of these are already drawn in a convenient way, where we already have these blown up. Now we just need to worry about assigning priority. So when we're trying to assign priority for these, again, atomic number that are 1 bond away from the asymmetric center. And then if it's tied, you go 1 more step. We're always trying to break the tie. So you're taking a step in the direction that has the highest atomic number, at all times. And so let's look at an isopropyl group versus an ethyl group, a methyl-ethyl versus just an ethyl. Intuitively, we could look at these and say, well, there's more carbons on the methyl-ethyl group, so that's probably higher priority. But to actually show it, you would say, okay, well, the first thing that's attached to the asymmetric center is a carbon and a carbon, so they're the same. You take 1 step further out, and you get to another carbon, and you get to another carbon, still the same. You go 1 step further, you get to a hydrogen, and you get to a hydrogen, still the same, and we hit the end of the molecule, right? When that happens, you go back to the beginning, you do it again, except you have to take a different route. Right, so look at this as, I'll draw the complete structure. So we have our methyl-ethyl group versus the ethyl group. If we're deciding priority between these, the first step is carbon, second step is carbon, third step is a hydrogen, and we hit the end of the molecule. So we do it again. but you have to go a different route this time. First step is a carbon. Second step has to be a hydrogen, because you have to take a different second step. Right? So because we have two different steps that both take us to a carbon here, and only one that takes us to a carbon here, this means the isopropyl is going to have a higher priority. So you'll get better at this, but essentially what you're usually going to be looking for is, what's the most complicated thing? If it's all just carbons and hydrogens, it's usually going to be whatever is the most complicated. So you'll develop a bit of an intuition, but this is the process is, take steps, try to break the tie. Before we can assign full priority though, we have to go CH2Br is down here, and a methyl down here, right? So what's our highest priority going to be? One with the bromine. They are all carbons on your first step, right? So they're all tied. The next step is either another carbon in these two cases, it's a hydrogen for this case, or a bromine in this case. Bromine's the biggest, highest atomic number. So bromine is going to be the highest priority. What's lowest priority? Methyl. So again, they're all carbons on the first step. The second step for this one has to go to a hydrogen. So 1 and 4. 1 and 4 are usually going to be the easiest, in my experience. And then 2 and 3 gets tricky. In this case, isopropyl and the ethyl. So now, what do? We want to rotate it so that number 4 is into the board. So again, usually the ones that are easiest to keep constant are going to be the ones that are already flat in the plane. It's easiest to visualize that way. So we could either, if we keep 2 in the same spot, we can twist everything else, put 4 in the back. So we'd be taking this and twisting it this way. And so 4 goes into the back, 1 moves over here, 3 comes to the front. And when you redraw these, you don't need to redraw the whole thing, you can just use the numbers. We kept 2 where it was. We rotated so that 4 was back. What was 3 is now coming out towards us. And 1 moves over to the left. So again, that's out of the 3 distinct steps, that's the hardest one to get. Learning how to assign priority takes a little bit of practice, but it's pretty easy once you get the hang of it. This is the one, the rotating is the one is the trickiest to see what's happening. And then once we do this, you just draw your arrow. 1, 2, 3, 1, 2, 3. So that tells us that it's R. Because 1, 2, 3 goes clockwise. So we want to know the full name of this molecule. We figured out that it's R. Now it's almost a separate process to take something that's blown up like this and redraw it in a way where we can find our longest continuous carbon chain. Although I suppose we have, it's doable from here. The longest continuous carbon chain that has the bromine. 1, 2, 3, 4. I was redrawing this, looked like 1, 2, 3, 4 with the bromine at the end. And then on carbon 1, or sorry, on carbon 2, there's a methyl and an ethyl. And then carbon 3, there's another methyl. So remember, longest continuous carbon chain that has the bromine. So our complete name here would be 1 bromo, 2, 3 dimethyl, and 2 ethyl. Butane. And then we just throw R on the front. For whatever reason, R usually gets written in parentheses. I'm not going to be picky about that, but that's generally how you see it written. If you forget the parentheses, it's no big deal.
Does S not get parentheses?
S gets parentheses too. We're not that discriminating when it comes to right-handers versus left-handers. So again, the rest of our name is the same as we've been doing it. Longest continuous carbon chain, name all your branches. It's just that because we have an asymmetric center right here in the middle, we need to say specifically is it R and S. And the way I drew this, I was not being all that careful to keep the same configuration, so I didn't say which one was coming out towards us and which one was going away from us. I was just trying to redraw it so that I could figure out where all my branches were. If I was trying to redraw it and make sure I had the exact same molecule, I would need to make sure that I got the methyl group going one way and the ethyl group going the other way. One out towards us, one away from us, and that's a little bit trickier to do quickly.
And so when we draw from a blown up, is the carbon chain always going to start at the highest priority?
That's an interesting question. That's an interesting way of framing it. The carbon chain is not always going to start at the highest priority. The highest priority will always be on the longest continuous carbon chain.
Okay.
I think I can say that, yeah. If it's drawn as a skeletal structure already, it's easy to come up with the parent compound, right? Then it's just a matter of figuring out R versus S. So let's practice that with the middle one. Get your parent molecule and then redraw it blown up so we can assign priority. And I'm going to get some markers that aren't quite so dead.
Man, we got lots of stuff up today, dude. We got Miranda here to give us a check.
Remember to put an AC over on the top there. Yeah.
Dude, if you just kept your pot, you would do that back this minute. Fire turn up. This is the season of fire, right? The Bureau of Flames.
No, we're done with that now.
Fire control system in there.
Is there?
Yeah, we really got a little sprinkle on.
Yeah. You just gotta check if it works or not.
So, parent molecule, easy enough, right? Remember counting from the lowest side. So 2-chloropentane.
Yeah.
If it was 3-chloropentane, we would have 2 identical substituents attached to that carbon, right? So the 2 ethyls would be identical. So we wouldn't have any stereochemistry, we wouldn't have an enantiomer. But because it's 2-chloro, and we can tell the difference between a propyl group and a methyl group, we need to worry about whether it's R versus S. So if we redraw this, the easiest thing to do to make sure you don't mix something up, because when you redraw this is also a place where people get tripped up. Redraw everything in the same exact position, just more explicitly. Don't change which direction your bonds are pointing, or you run the risk of accidentally turning it from R to S. Right? And then you can go through the whole rest of the process correctly and still get the wrong answer. And the nice thing is it's 50-50 shot, right? So you can only be so wrong, but at the same time, just don't move anything that you don't have to. Keep everything in the same spot. And a lot of times we wind up writing our condensed structure backwards, so to speak, so that we wind up with the bonds being drawn between the right atoms. So a lot of times you'll see me write H3C instead of CH3. It's so that it doesn't look like I'm drawing a bond straight to a hydrogen. So where am I going to put the hydrogen? Where does the hydrogen go? Out of the board. Physically, spatially on the board, which direction should I draw it? It's going to be a wedge next to the chlorine. Your two that are if you have two that are flat, your other two that's going into the board and out of the board have to be right next to each other. That's another place that people can get messed up, because if I do this, now all of a sudden I could get the wrong, when I count 1, 2, 3, I could get it mixed up, right? Because it's supposed to be up here. All right, let's assign priority. What's highest priority? Chlorine. What's lowest priority? Out of a methyl and a propyl, what's higher priority? So, again, however it makes sense to you, the biggest thing is we're treating this as a physical object. So we can't just erase things and rewrite them wherever we want. We have to move the whole object. So if we want hydrogen to be going away from us, we could take this, we could twist the whole thing. If we took this, if the hydrogen's my index finger here, and my forearm is this bond, you could do that, right? So what was down at the bottom would go up to where the hydrogen is currently. So we're rotating around that bond. And really, and when you do this on the test, I totally expect to see you guys making weird arm motions and things like that. That's totally fine. You don't have to be able to do this totally mentally. In fact, I've never really thought about this. I don't necessarily see a problem in even letting you have your modeling kits in front of you. It'll be slow, potentially, but if you have one already set up to have 4 different substituents, like Ryan has right there, you just have that in front of you so that you can visualize things better. I don't think I have a problem with that, especially while you're first getting used to it. The other way, so let's finish this up and then I'll teach you another way to visualize this one. So when we finish rewriting this, we wind up with 4 is in the back, 1 is now down here. Our methyl, which was, stick to just doing the priorities. Our methyl is up here. Priority 1 down here, and 2 didn't move, right? Draw 1 to 2 to 3, and we get clockwise, right? So R, 2-fluoropentane. There's one other option when it comes to this. If you wind up with your highest priority sticking, or your lowest priority sticking out towards you, then we're effectively looking at the back side of the clock, right? If 4 is our lowest priority, if a hydrogen is our lowest priority and it's looking out towards us, we want it being away from us, we're looking at it backwards right here, right? So in the other, and sometimes this is more helpful for some people than others, if you leave this molecule exactly where it's drawn and put your frame of reference behind the board, if you step through the board and look at it backwards, if I draw 1 to 2 to 3, the way it's drawn here, and now if I take this and I put myself behind the board and move my finger the same way, that's still R, right? To me, because I'm behind the board. Right, so we're moving a physical object. If you're looking at the back side of the clock, you can turn the clock around, or you can walk around and look at the clock from the other side. So for some people, visually, that's more helpful. And the other advantage of that is you don't have to redraw either. You wind up with priority 4 sticking out towards you, draw your 1, 2, 3 arrow, step through the board, and it's backwards compared to looking at the back of the clock. Right, in both cases, we draw the arrow on your paper a different direction, but if you visually think about this as a three-dimensional object, it's because we're looking at the back of the clock here versus the front of the clock. It's still R in both cases, right? If the idea of stepping through the paper, looking up from the other side is hard, I mean, in theory, if you drew this on a piece of binder paper, draw your arrow, look at the back of your piece of binder paper. The direction your arrow is going should be the right way, because that's effectively the same thing that you just changed, right? You're looking at it from the opposite side now. It's just tricky. Seeing these things in 3 dimensions from a 2-dimensional drawing takes a lot of practice. So for this last example over here, we don't know how to name alcohols yet, OH groups, so we won't worry about the whole name here. Let's just figure out R versus S. What's our highest priority? The OH. Why, Sarah? Because you only look one step away first. So bromine is higher atomic number, but your first step goes to a carbon versus an oxygen. All right, so oxygen is the highest priority. And again, drawing this out, it's already blown up for you, so just try not to move anything. So highest priority is the oxygen. All three of these go to a carbon. So we take one more step. Next step here goes to a bromine. The next step for both of these goes to another carbon. So this is a good molecule to use as an example, because it's not just about what's the highest atomic number, period. And it's not just about where there are more carbons. Because if it's just about where there were more carbons, this would be higher priority than the bromomethyl up here. Right? It's take those steps. Every step is a tiebreaker. And we play by NHL rules here. You go until there's a winner. Okay, it's playoff rules. You go until there's a winner. So you can have 5 overtimes in a row if you need to. So the ethyl with the chloro on it beats out the regular ethyl, because they both go carbon, then a hydrogen, or a chlorine. Chlorine's bigger than hydrogen. And so if we're going to try and we want to put 4 in the back. The one that makes the most sense to me, to keep this one the same, since it's in the plane of the board. You don't have to keep the one that's in the plane of the board stationary, but sometimes it's easier to visualize. We can keep number 1 stationary and spin these 3 like a rotor, but that's a little bit harder to visualize for most people. So it just happens, this has just been a coincidence that it's been number 2 every time that we're keeping stationary. That's not always going to be the case. That's just pure luck with these examples. So if we keep 2 stationary, number 4 is my thumb, and we're going to twist it that way. Right, so 2 stays in the same spot, 3 comes out towards us, 1 goes over here, and 4 is in the back. Once you do this 5 or 6 times with the models in front of you, you start being able to see it's the same rotation every time. You start to be able to visualize it a lot better. And so you might not even need this on the test, but it's still a nice safety blanket to have, to know that you're not going to get into, all amped up on adrenaline and completely forget how to do it, right? You still have your models in front of you. So 1 to 2 to 3, R. Again, if you find it easier to move yourself rather than the molecule, in order to put 4 in the back, you would need to look at it from up here, right? You can see it visually. 1 to 2 to 3 would be going like this. I'm standing in the plane of the board looking down at this object. I'm still going clockwise when I count 1 to 2 to 3. And so you can do it by shifting your frame of reference so that 4 is pointed away from you, so that you're looking at the front of the clock. No matter where 4 is, that works. Treating it like a propeller and twisting it, though, and looking at it head on seems to be what most people do the best. I have about 1 or 2 every year that prefer to move their head instead of the molecule, and that's fine. Right, that's effectively, if the red is our lowest priority here, instead of looking at it head on and then twisting it to do that, I'm stepping around over here to look at it this way and keeping this in the same spot. Right? 3-dimensional molecules on 2D paper is hard. I get that. All right.
What do we name that guy in the end?
I didn't write out the whole name for it because we don't know the rules for naming alcohols yet.
That's right.
If I was naming this thing myself, the longest continuous carbon chain that has the bromine, the OH, and the chlorine all on it goes 1, 2, 3, 4. So it'd be a 1 bromo, 2 ethyl, 4 chloro, 2 butanol. So it's, the root name would be butane, except if it's an OH group, we put OL at the end instead of just the E. You have to say where that is. That's on carbon 2. There's also an ethyl on carbon 2. There's a bromine on carbon 1. And there's a there's a chloro on carbon 4. And then, don't forget your R in there. R, 4 chloro, 1 bromo, 2 ethyl, 2 butanol. It's a long name, but it's still just following our rules, right? Same thing we've been doing. Well, except for the OL, but we'll get there. All right, last concept, since I know we're about out of time. If you have 2 asymmetric centers, you have to do this twice. Because each asymmetric center could be R or could be S.
It won't be both though, right?
It won't, well, this carbon has to be either R or S. And this carbon has to be either R or S. So you can have R and S in the same compound, but just not on the same carbon. So this compound, if this is one, we could name this 1R2S. If there's more than one asymmetric center, we do it twice. And then you just stick a number on in front of which one you're talking about. And so that example that we used that was on the quiz, that it was cis dimethyl cyclopentane, right? If it was trans dimethyl cyclopentane, you would have something that looks like that. Each of those carbons is an asymmetric center. Each of those carbons has 4 distinct things attached to it because the ring, we can now tell which direction you're going around the ring, right? You're going towards the other methyl or away from the other methyl. So this compound would actually have 2 distinct stereocenters, 2 asymmetric carbons. So we would have to name it as 1R2R or 1R2S. We would just have to go through this process for each of these, for both of these carbons. Okay, but the process doesn't change. And the one concept that I want to impress, and I'll say this again later, it's one of those things that takes more than once hearing it. These 2 are mirror images of each other, right? We flipped both of the stereocenters. These 2 are mirror images of each other. We flipped both of the stereocenters. 1R2S and 1R2R are isomers, but they're not mirror images because we only flipped one of the 2 stereocenters. And so that's what we call a diastereomer. I'm going to not be able to spell it out. A diastereomer means that it's a different stereoisomer, but it's not a mirror image. Because one of them flipped, but the other one didn't. Right? And again, I will say that again on Thursday when we start class, and we'll do more practice. I didn't spell it right, diastereomers. Right, but this is the next, are they the same or are they something else? They can make mirror images, stereoisomers that aren't mirror images, or they could be the same molecule. All right, so we'll keep practicing with this.
Sinister Diastereomer. Let's see. That is good scalp.
These are actually chemical names, are valid Scrabble words.
Oh.
The highest scoring Scrabble word that you can ever get
Yeah.
is